Dear students, welcome to EPG Pathshala. I am Dr. Rajkishore Sharma from Chemistry Department, University of Delhi. Today we are going to discuss about the module Instrumentation of Photoelectron Spectroscopy under the paper of Surface Analytical Techniques 2. The main goal in PES is to gain information about the composition, electronic state, chemical state, binding energy and more of the surface regions of solid. The key points in PES is that a lot of qualitative and quantitative information can be gathered from the surface region of solid. The focus here will be on how the instrumentation of PES is constructed and to understand the construction of PES instrument. To choose an appropriate analyzer of a given system is important, and when to use either XPS or UPS to study the system is also necessary. So today we are going to discuss the following topics. We will start from the parts, then we'll discuss the working of an electron spectrometer, we'll talk of light source, X-ray tube, gas discharge lamp, synchrotron radiation, electron gun, energy analyzer, specific analyzers, vacuum UV source and the target sample. The basic requirement of a photoelectrospectrometer is shown in the image. A source of fixed energy radiation is an X-ray source of XPS or typically a helium discharge lamp for UPS. An electron gun, then an electron energy analyzer which can disperse the emitted electrons according to their kinetic energies and thereby measuring the flux of emitted electrons of a particular energy. A high vacuum environment is used to enable the emitted photoelectrons to be analyzed without interference from gas phase collisions. PS is rather picky when it comes to keeping the surface of the sample clean and keeping the rest of the environment free from interferences from things like gaseous molecules. The high vacuum that are used always an ultra high vacuum UHV environment. An electron detector is used. The general description of PES is shown in this slide. Now we will see how an electron spectrometer works. First of all, sample is irradiated by an excitation beam which can be electrons, ions, X-rays or low energy photons. Then separation of ejected electrons according to their energies. After that, detection and counting of electron is done by the detector. And finally, the data is recorded. There are several methods for sample preparation. First one is in situ cleavage. In this technique is very good method for exposing a new fresh clean surface from single crystal of most semiconductors, insulators and layered compound samples. Most metal samples can easily be prepared as a thin film by means of in situ evaporation after careful and thorough outgassing of the filament. Second method is sputtering from a material target onto a substrate. This is another useful technique to prepare thin films of the samples. Argon gas is usually used to set up the glow discharge. In this technique, amorphous films are obtained unless the substrate is heated or the sample is annealed. This technique is also feasible for insulators and some semiconductors provided sputtering is used to compensate for the immediate buildup of surface charge. Next technique is ion bombardment cleaning. Ion bombardment cleaning should also be mentioned here as another method of obtaining clean surfaces in which a focused beam of ions, usually argon at 5 into 10 to the power 6 torr is accelerated into the specimen surface, the sputtering of surface layers. This method results in amorphous surfaces containing argon atoms, which tend to get embedded into the surface. Therefore, annealing is needed. Alloys and intermetallic compounds are difficult to cleave or to sputter off because of possible different yields for the various components. Light sources. These could be X-ray tubes, gas discharge tubes, synchrotron radiation. Due to the geometric considerations, it is not possible to mount all the three sources on a device. Thus, these devices are designed to be used interchangeably with the same electron analyzer. While many components of instruments used in PES are common to both UPS and XPS, the radiation sources are one area of distinct differentiation. The radiation source of UPS in a gas discharge lamp, with the typical one being an helium discharge lamp operating at 58.4 nanometer, corresponding to 21.2 electron volt of kinetic energy. XPS has a choice between a monochromatic beam of a few micron or an unfocused non-monochromatic beam of couple of centimeters. These beams originate from X-ray sources of either magnesium or aluminium source, giving off about 1486 electron volt and 1215 electron volt of kinetic energy respectively. For a more versatile light source, synchrotron radiation sources are also used. Synchrotron radiation is especially useful in studying valence levels as it provides continuous polarized radiation with high energies greater than 350 electron volt. The main thing to consider while choosing a radiation source is the kinetic energy involved. The source is what sets the kinetic energy of the photoelectrons. So there needs to not only be enough energy present to cause the ionization, but there must be an analyzer capable of measuring the kinetic energy of the released photoelectrons. About the X-ray tubes or the production of X-rays. The X-rays are produced in X-ray tubes. X-ray tube is a vacuum chamber consisting of two metal electrodes. On heating tungsten filament cathode, which is present at high negative potential, electrons are produced and are accelerated towards the anode, which is present at ground potential. The potential of the anode is grounded. These high velocity electrons then collide with water cooled anode on striking the anode. Loss of energy occurs, which is manifested as X-rays. Less than about 1% of electron beam is converted to X-rays. Rest is dissipated as heat in the metal anode. Diagram of the X-ray tube is shown on the screen. The synchrotron radiation. Synchrotron radiation is a name given to the radiation which occurs when charged particles are accelerated in a curved path or an orbit. Classically, any charged particle that moves in a curved path is accelerated in a straight line path will emit energetic and electromagnetic radiation. Various names are given to this radiation in different contexts. Particularly in the application of circular particle accelerators like synchrotrons, where charged particles are accelerated to very high speeds, the radiation is referred to as synchrotron radiation. This radiated energy is proportional to the fourth power of the particle speed and is inversely proportional to the square of the radius of the path. It becomes the limiting factor on the final energy of the particle that are accelerated in electron synchrotrons like LEP or CERN. In other contexts, like the detector arrays in accelerators, it can be detected and used as an aid to analyze the products of the scattering events in the accelerators. the gas discharge lamp. Out of all the sources, we will discuss gas discharge lamps in brief. As shown in the slide, the gas discharge lamp is the radiation source for UPS, with the typical one being as helium discharge lamp operating at 58.4 nanometer, corresponding to 21.2 electron volt of kinetic energy. The electron gun. In PES experiments, electron gun can also be used in conjunction with X-rays to eject photoelectrons. There are a couple of advantages and disadvantages of doing this. However, with an electron gun, the electron beam is easily focused and the excitation of photoelectrons can be constantly varied. Unfortunately, the background radiation is increased significantly due to the scattering of falling electrons. Also, a good portion of substances that are of any experimental interest are actually decomposed by heavy electron bombardment, such as that coming from an electron gun. A sample image of the electron gun is shown in the slide. State of the sample, the physical state, that is solid or gas, decides the need and design of the gun. In both the cases, electron guns operate with the filament at high negative potential. The electrons are drawn out through a small orifice towards the first structural element, which is at ground. The final kinetic energy is determined primarily by the voltage on which the filament is floating to the total energy. For the extracted electron beam, the resistance is dropped across the filament by the use of the heating filament, resulting in a slight broadening of the kinetic energy distribution and is caused by thermal tailing. The energy analyzers. There are two main classes of analyzers well suited for PES application, that is kinetic energy analyzer and deflection or electrostatic analyzer. The kinetic energy analyzers have a resolving power of capital E upon delta E, which means the higher the kinetic energy of the photoelectrons, the lower the resolution of the spectra. Deflection analyzers are capable to separate out photoelectrons through an electric field by forcing electrons to follow different paths according to their velocities, giving a resolving power E upon delta E that is greater than 1000, since the resolving power of both types of the analyzer is E upon delta E. The resolution is directly dependent on the kinetic energy of the photoelectrons. The intensity of spectra produced is also dependent on the kinetic energy. The resolution and the intensity of the spectra is directly dependent on the kinetic energy of the photoelectrons. The faster the electrons are moving, lower the resolution and the intensity. In order to actually get well resolved useful data, other components must be introduced into the instrument. To improve the resolution and intensity of the system, optics is added to PES instrument. Electron optics are able to de-accelerate the photoelectrons through retardation of the electric field, and this energy is known as pass energy. The de-acceleration helps in raising the resolution but lowers the sensitivity also. The specific analyzers. Within the broad picture of two main analyzer classes, there are a variety of specific analyzers in existence that are preferentially used in photoelectron spectroscopy. These are cylindrical deflection analyzer, the spherical deflection analyzer, the plane mirror analyzer, the cylindrical mirror analyzer. All the analyzers are explained in more depth under the spherical deflection analyzer topic. First of all, we will study plane mirror analyzer. We call it PMA. PMA is the simplest type of electric analyzer, or also known as parallel plate mirror analyzers. These analyzers are condensers made from two parallel plates with a distance small d across them. Parabolic trajectories of electrons are obtained due to the constant potential difference. Constant potential difference, that is capital V, between the two plates. In order for transmission to occur, the potential must be V is equal to E naught into D upon EL naught, where E naught is the kinetic energy of the electron in electron volts and small e is the charge of the electron. L naught is shown on this slide. To obtain better focus, the electron entrance and exit angle is capable of being shifted to 30 degrees. But this is not necessarily a good idea as it sacrifices transmission instead. Second is the cylindrical mirror analyzer, and we call it CMA. CMAs are advantageous over PMAs. They employ 2 theta geometry to overcome the low transmission with the PMA. A CMA consists of 2 cylinders, having a potential difference V between them. The entrance and exit slits are all contained on the inner cylinder. Here, V is equal to 1.3 times E naught ln into the ratio of R out upon R in, where L naught is equal to 6.1 into R in and E naught is in volts. They are good for applications that require a high sensitivity with only a moderate resolution. Cylindrical deflection analyzer or CDA. CDAs consist of 2 cylinders spanning a 127 degree angle. It is the reason that CDAs are sometimes called 127 degree analyzers. The potential difference in a CDA is 2 volts, which is given as 2V is equal to E naught into the potential difference in a CDA is actually 2V, which is given as E naught into the ratio of R in upon R out. So E naught into R in upon R out, where E naught is the energy of incoming photoelectrons in electron volt that are focused. These analyzers have high resolution, however, the transmission is low. It is called 120 degree analyzer because it focuses when a cylinder span is at an angle of 127 degree. Last one is the spherical deflection analyzer, that is SDA. SDAs are similar to CDAs, but they consist of 2 concentric hemispheres instead. In an SDA, the transmission of photoelectrons with initial energy E naught occurs along with a path where R naught is equal to R in upon R out divided by 2. Potential of the outer sphere is V out, which is equal to E naught into 3 minus 2 into R naught upon R out. Potential of the inner sphere is V in is equal to E naught into 3 minus 2 into R naught upon R in, where R naught is R in plus R out divided by 2. The slits in a spherical deflection analyzer define the acceptable range of entrance and exit trajectories of a photoelectron may have while entering or leaving the analyzer. The photoelectrons that do not make it through the entrance slits will then only exit if they follow a specific curved path down the middle of the 2 hemispheres. The path they follow has the correct energy for an exit to occur and is determined by the selection of V in and V out. Photoelectrons that are of higher or lower kinetic energy than what is defined by the hemisphere will be lost through the collision with the walls. Now we will discuss about the fixed analyzer transmission mode and fixed retardation energy. The fixed analyzer transmission mode is called FAT and fixed retardation energy mode is FRE. The resolving power of these analyzers is proportional to the radius of the inner and outer hemispheres. These analyzers are also capable of running in 2 separate modes when coupled with an optical system: fixed analyzer transmission mode or FAT and fixed retardation mode FRE. First is the fixed analyzer transmission mode. In FAT mode, the lens either retards or accelerates the electrons so that all photoelectrons enter the analyzer with the same kinetic energy. For this to occur, The analyzer is also arranged so that only photoelectron of a specific fixed kinetic energy will pass through and reach the detector. In this case, the lens is scanned for different energies. Second one is the fixed retardation energy mode or FRE. In FRE mode, the lens only retards the photoelectron and it does so in a uniform manner, causing all photoelectrons to be reduced in energy to a fixed value such as 15 electron volt or 30 electron volt or whatever energy is desired. The hemispheres of the analyzer here have a potential difference between them. This potential difference is varied so that the photoelectrons of different kinetic energies can reach the detector. The more common of these two modes is the FAT because it provides a greater signal intensity at low kinetic energy and is also make quantification of the spectra simpler. Now, the vacuum UV sources. The most important source of radiation of photoelectron spectroscopy of the outer shell are vacuum UV lamps. The spectra created in these lamps contain sharp lines. These are formed as a result of de-excitation of the excited free atoms or ions. These lines are intense, sufficiently energetic to eject electrons from the lesser bound orbitals of most molecules and have a small natural width of only a few millivolts. Other sources used are helium-2, helium-1, neon and argon-1. Target sample. In principle, any solid or gas sample can be studied by electron spectroscopy. However, liquids require very special techniques. In the case of solids, the source volume as well as the analyzer is kept at lower pressure. Gas samples can be studied by maintaining the source volume at moderate pressure with the help of a differential pumping. Generally, liquids will simply evaporate before measurement can be made. However, liquids with low vapor pressure, which is a practical limit is about 1 millimeter, can be studied if differential pumping is adequate. Even though electron spectroscopy cannot be used to study everything, there is a rather wide world of chemistry that can be investigated. We shall divide this section on target samples into three sections, that is gases, solids and condensed vapors or liquids. Since each of these different types of targets has its own particular requirements. Now the gases. One of the main problems in studying the gases is that a high pressure is desirable in the region of ionization in order to obtain reasonable signal strength. At the same time, the pressure should be sufficiently low so that the electron does not suffer a collision, particularly an inelastic one, between the time it is ejected from the atom or molecule until it strikes the detector. This is accomplished to a large extent by the differential pumping that is afforded by the entrance slit. The gas to be studied is leaked into the source volume. For a typical slit size of 1 cm into 0.2 mm, a differential pressure of 10⁻³ can be maintained if the spectrometer is being pumped at the speed of 100 liters per second. About the solids. A solid target in general is mounted in a fixed position as close to a photon source and entrance slit as possible, or close to an optical system so that the ejected electrons are transmitted into the analyzer with high efficiency. In photoelectron spectroscopy of solids, the choice of the angle between the direction of the incoming photon and the direction of the outgoing photoelectron is generally not critical. Although the distribution of photoelectrons ejected from a pure S wave is peaked in the direction perpendicular to the incoming beam. According to sign, to theta, the angular distribution of electrons ejected from molecules is usually more isotropic. The detector system. As a consequence of having passed through the analyzer, electrons of a given kinetic energy are spatially separated from the electrons of different energies. These electrons must now be detected and recorded together with information which determines their energy, such as the electrostatic or magnetic fields applied to the analyzer. This information must be stored and some method devised for scanning over a spectrum of electron energies. Finally, one may wish to process the data for plotting, curve fitting, subtracting background, etc. There are two types of detectors, that is single channel detector and position sensitive detector. Now we will discuss scanning of the spectrum. For a given setting of the analyzer, electrons of one kinetic energy are counted by the detector. To scan over the spectrum, the electrostatic or magnetic field is altered, and the counting rate is determined as a function of the field, which in turn is proportional to the kinetic energy of the electrons. Another way is to couple the output of the multiplier to a strip chart recorder. A better but more expensive method is to scan the spectrum with the aid of a computer, which advances the voltage in discrete steps and stores the data. The total number of counts being recorded at each incremental step in a given channel, the data once stored can be processed by subtracting background, by assigning errors, and by deconvolution of the overlapping peaks. So, in order to summarize what we have learned today, the basic requirement for a photoelectrode spectrometer: a source of fixed energy radiation, an electron gun, an electron energy analyzer, a high vacuum environment, an electron detector. While many components of the instrument used in PES are common to both UPS and XPS, the radiation source are one area of distinct differentiation. The radiation source of UPS is a gas discharge lamp, with the typical one being an helium discharge lamp operating at 58.4 nanometer, which corresponds to 21.2 electron volt of the kinetic energy. XPS has a choice between a monochromatic beam of a few microns or an unfocused non-monochromatic beam of a couple of centimeters. These beams originate from X-ray source of either magnesium or aluminium, giving off about 1486 electron volt and 1258 electron volt of kinetic energy respectively. In PES experiments, electron guns can also be used in conjunction with X-rays to eject photoelectrons. With an electron gun, the electron beam is easily focused and the excitation of photoelectrons can be constantly varied. There are two main classes of analyzers well suited for PES: kinetic energy analyzer and deflection or electrostatic analyzers. Since the resolving power of both type of the analyzers is E by delta E, the resolution is directly dependent on the kinetic energy of the photoelectrons. The intensity of the spectra produced is also dependent on the kinetic energy. Within the broad picture of the two main analyzer classes, there are a variety of specific analyzers in existence that are used in PES, that is, cylindrical deflection analyzer, the spherical deflection analyzer, the plane mirror analyzer, and the cylindrical mirror analyzer. Thank you.